Hey everybody, it's Siobhan and welcome back for another Game Programming Concepts Talk. Today we're going to be talking about artificial intelligence, or AI, in games. And I feel like there's kind of a lot of confusion around this, so I want to kind of simplify it to declutter some of what we understand about what AI is in games. But first, I feel like we need to answer the question, which of these is the best AI movies? Is it Deus Ex Machina by Alex Garland? Is it Chappie by Neil Blomkamp? Is it The Ghost in the Shell by Masamune Shiro? Or is it Her by Spike Jonze? No, I'm kidding, of course. We're not talking about that. In fact, I do want to bring that up, because there's this kind of concept. We hear AI a lot, and we hear about computers, we hear about robotics and this kind of stuff. You hear things like machine learning, or neural networks or something like that, or whatever. I want to just point out that when we're talking about AI in games, we are usually not talking about these things yet, at least, right? So maybe eventually we're going to bring those types of things up. But no, we're not trying to create lifelike artificial intelligence that's supposed to resemble emotions of human beings. In fact, we don't want our enemy NPCs to have feelings, right? It would be considered inhumane if you killed an enemy NPC that learned human emotions, right? All right, you can make your game about that if you want. That's a freebie. Anyways, I'm kidding. But the thing is, there are plenty of videos online about artificial intelligence and the different algorithms, and they kind of go into more depth about exactly how those work. And, I could maybe create separate videos about that, but that's not what we're going to be talking about today. I'm really going to mostly just be giving a rant, right? Almost like an educational rant. I can't say edurant because I think that's like a copyrighted drug or something. But that's kind of what it is, right? Because I want to give you the pragmatic context for artificial intelligence when it comes to game development, kind of as a whole, and then tie it into how programming, has to do with that. But I know you're here for my hot takes, and I'll go ahead and give you a hot take now. In my personal opinion and in my experience, AI is more of a game design type of task than it is a programming task. I mean, it's definitely a programming task, but I feel like a lot of it's just rooted in the game design. And so let me kind of talk a little bit. So I've heard a lot, I'm just going to go ahead and move the screen here. I've heard a lot of different game pitches, right? And many of these game pitches are from novice game designers, and that's fine. Everyone has to kind of figure their self out at some point. But I hear this whole term enemy AI and all that kind of stuff just thrown around willy-nilly. Or sometimes they'll just kind of start describing some kind of mechanic that implies there's some kind of AI, but they don't really talk about it. So for example, let's say that one of these game designers will say, I want to make a stealth game, right? I want to make a stealth game where you have you have to perform actions covertly in order to avoid suspicion, suspicion from other NPCs or enemy suspicion, and you have to cover your tracks, and destroy evidence or something like that. Okay, and then let's go ahead and just start drawing something so that we can have some fun here. All right, so we have this character. It's trying to avoid suspicion, so is wearing a mask. Something inconspicuous like a mask, right? And he got that little smirk. I'm gonna avoid all sorts of suspicion. You got your character, okay? But here's the thing about it. Then they'll continue by saying I'm gonna need some really skilled programmers for this game because there's gonna be a lot of AI and stuff like that involved, right? Because they hear the term, right? But see, the thing is, then you ask them can you explain to me, what do you mean by, avoid suspicion? What does that mean, right? Can you describe the play-by-play of, a game moment in this particular game? Can you describe a sequence? I just have to better understand what this means. What does it mean to, destroy evidence or whatever you're doing that's supposed to thwart the enemy's artificial intelligence or something like that. And then the response is sometimes well, we haven't prototyped it yet or, whatever. But like I said, we're going to need some pretty advanced programmers to start figuring that out. It's like, I don't know about that. Because the thing is that AI, when we talk about AI, it often boils down to a collection of patterns that are triggered by predetermined conditions. Okay? Emphasis on predetermined conditions, right? These are patterns that are designed for a particular system or for a particular character. And so when we're talking about implementing these types of patterns, this collection of patterns triggered by predetermined conditions, we are typically going to jump for this delightful structure called a finite state machine. You might have heard this kind of idea, and you might be like, what? That's like elementary or something like that. But you know what? Even in the most like super advanced jujitsu, programming that you might be doing, it kind of boils down a lot of ways to just the finite state machine, right? Now, sure, you might have some pretty advanced structures involved in creating the state machine so that it's, generalized and it's well organized and you're not just creating like a whole bunch of if, else, if statements or something like that. But generally speaking, it boils down to this idea of a finite state machine. So what am I talking about? So coming back to this game, the player, so the designer, often will say like the enemy chases the player. Okay, so enemy chase the player. What does that mean? So we have a character. Let's say this is a platformer, just to make this simple. And then you've got this enemy called, mushroom monster, some kind of thing called mushroom monster. His little teeth and his little big feet, mushroom head character. And see, the thing about this mushroom head character, it's a one-dimensional game, right? So the character can only move left or move right. Okay, so when this says the enemy chases the player, what in the heck does that mean? Well, perhaps you would define your state machine with the following pseudocode. You would say something like, if the player X position is less than the enemy's X position, then enemy is in the move left state, right? So that's the state. So when the condition here is that when the player's X position is less than the enemy's X position, therefore being to the left of the enemy is going to be in the move left state, right? And then otherwise, if the player's X is greater than the enemy's X, then the enemy will be in the move right state or something like that. You could simplify it to some kind of state machine in this way. It's very simplistic. And then you would add another layer, and then when the enemy is in range, it attacks the player. Okay, so then you add just a little bit more, right? So you have this kind of movement thing, but you also say, if player if distance from player to enemy is less than aggro distance or something like that, then enemy attack left, I guess, because we're in this kind of sub part of this. So is it now in the attacking state if you're within that range, right? So let's say, when we were talking about distance, we're typically just well, in this case, distance is just like horizontal, right? We're just talking about X. And then there's this kind of aggro range that we're checking for if it's within. If it's distance from it is less than the aggro distance, then we perform an attack, right? So this is a pretty simplistic system, but you're not the one who chose this idea of an aggro range and the enemy attacking and all this kind of stuff. Right, that's typically something that is designed by the game designer. And this all might seem pretty obvious, but here's the thing: this is a pretty simplistic system, but it doesn't answer all the questions. And see, the questions are mostly design questions, right? Because you could create the game, but then the game is incomplete. It's like, okay, sure, this is so far so good, except there's a bunch of questions that will have to be asked. So for example, what if the player is off the cliff, or on a different cliff? Does the enemy fall off the cliff while chasing the player? Is that something that the enemy can do? That's a designer question, right? Is there any lag time between the enemy attacking? I guess this mushroom character does like a big old bite attack. It's like, chomp. And of course, that's what you would expect a little mushroom character to do, something like that. Lunges at you. Anyway, so like, does the enemy attack while they're moving? Like, does it move and continue attacking? Is there like a lag time between attacking and then like moving again? Is there like some kind of range for when the enemy starts moving toward the player? Like, there's an aggro range for attacking, like the attack range, I guess. But was there like an aggro? I guess that's what I should have said for the aggro distance. Is there like an aggro distance also by which point the enemy will start chasing the player, or is the player always being chased by the enemy? If the enemy has this aggro range, what does it do while it's not being aggroed? Is it just sitting still? Is it moving? You know, if it's moving, then like, is it patrolling on like a particular predetermined path? Is it just like moving around randomly? Like, what is it doing? These are all design questions, right? And then like you get designers who are just like, and then we want boss fights. I want my whole game just to be a bunch of boss fights, right? They were inspired by Shadow of the Colossus. They're like, oh my gosh, I just want to make a game where everything is a boss fight, or something like that. But see, the thing is, like, it's another one of these types of things that are easier said than done in terms of design, because ultimately, I mean, also in programming, but in terms of design, it's like, you know, you're gonna have to come up with a different set of, you know, patterns and you know, movement and attack for each boss, right? If you want these bosses to be unique, right? And a lot of times bosses aren't unique, right? It's almost like they just kind of recycle the same boss, like in Donkey Kong Country. If any of you have heard of that game, they like, there's only like basically 3 bosses, you know, and like 2 of each are the same. Like there's like 6 levels, and 3 of those bosses are really just the same boss, but there's like slightly angrier than the other one. But in any case, what I'm trying to say is that they have to come up with each of those patterns, each set of patterns for each of those bosses. And frankly, once the programmer has all of those patterns and all the conditions to work with, then we can implement it into these different objects and systems. And you can quote me for this. The difficulty of the programmer's job is inversely proportional to the foresight of the designer. If the designer is somehow able to provide you all of the patterns and all of the conditions associated with these patterns, then you can design pretty robust code architecture around them. You can generalize these patterns to say that these are objects that are able to move or walk or attack or whatever they are, and so that you don't have to create these finite state machines that are unique for each type of character. It's pretty neat, but unfortunately, a lot of that depends on the designer. So anyways, I feel like a lot of this often comes down to the design. I'm saying the word designer a lot. Designer, 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 designer. All right, designer. Okay, now that we've gotten that out of the way, this whole idea of a finite state machine, because they get a lot more complex, right? Just like it moves, it's in the move state, it's in the attack state, and then it changes back to the move state, changes back to the idle state, whatever it is. These types of finite state machines, you know, they can get pretty complex. We'll talk about that a little bit later. But next, what I want to talk about is this whole idea is that the game designer will often say, like, okay, I want the enemy to chase the player, right? It's a really common type of game design mechanic. It's like, I want the enemy to chase the player. But what if the motion of the enemy is not one-dimensional, right? It's not just across one axis of motion. What if it's 2-dimensional or 3-dimensional? Right, so you have your game, your little stealth game. You got your little stealth character with your stealth bandana and your stealth smile, and you're in this, for some reason, I don't know why, but you're in a maze, right? Because that's what we always are in when we're talking about these types of things. I'm going to kind of move this over here. Our character is in some kind of, it's not even like a very complex maze, right? It's kind of like a box. And then there's like, you know, some different crates in the way or some trash. And you've got an enemy or someone who's going to suspect you, who's going to, you know, turn you in or something like that. It's some other character, like mushroom person, right? Turning you into the cops because you're doing some shady business. All right, so here's the thing about this kind of game, because it's like, sure, we want the enemy to chase the player, but here's the problem. The enemy, in order to go toward the player, has to go through This is embiggen this obstacle a little bit, has to go through obstacles, right? Have you ever played a game where the enemy is just kind of like sitting here, just like trying to walk through a wall? Yep, that's the mushroom character flattening into the wall. It's just kind of like trying, it's just cramming itself, like boom, it's just walking into the wall constantly. Yeah, the pathfinding algorithm was a little bit off, right? And so that's what I'm going to be talking about next. This whole idea of having the object, in this case an enemy, to get to its goal, in this case the player, it has to find a path to the player while going through an environment that has obstacles, right? And that's the idea of pathfinding, right? You may have heard of it. Okay, and so when we're talking about pathfinding, I'm just going to go over this very, very briefly, just so you have the terms. You have to often implement what's called a graph search, or sometimes called a graph traversal. How do I spell? Traversal algorithm. And these are kind of like fun, like people will throw these terms around so that they can feel smart. I'm kidding, because they have to do it sometimes, but also you find these types of things in like programming interviews or something like that, just so that the interviewer can understand your depth of knowledge in various programming topics. You're not going to ace any interview after watching this overview. Okay, I advise you watch other ones, but this gives you a high level, right? So we got graph search, we got graph traversal algorithms, and so let's talk a little bit about them. So when I say a graph search, I'm talking about how we break down this environment into a graph, right? So we essentially turn this into like a grid. Make this look terrible. In fact, what am I does? Like this program that I'm using right now is a graph, right? Like what am I doing? Perfect. Okay. All right, so we can consider each of these little points, these little nodes, to be positions that the enemy can be in. Like let's say the registration point for the enemy, whether that is the center or the bottom or whatever it is of the enemy, these individual points that you can hopefully see in the background of this whiteboard here represent the individual points that the enemy can be. Okay, so with that, it's like, how does it know which sequence of points is the best sequence of points, or a sequence of points that did my character just to get to the player? There might not be a sequence of points that's even valid, right? Because there's no path, right? That'll work. Like they're just entirely obstacles. You can't get to the player, right? And that is sometimes the result of one of these graph searches. Okay, but there are different algorithms to be able to calculate what that path is. One of those algorithms is called breadth first search. Okay, so BFS sometimes is what they like to call it. Breadth first search. It's kind of a tongue twister. So how does that work? Again, we're not going to talk about this in much detail. I'm just going to give you some high level stuff. Basically, breadth first search will finds the shortest path to the goal. Okay, the shortest path meaning like the fewest number of these little points in order to get to the goal, the shortest path to the goal. Great, so it finds the shortest path, which is, I guess, maybe what you want to do. It'll always find it. If there is even a path, but it can use a lot of memory. It can use a lot of memory. It uses more memory than perhaps other algorithms. Use a lot, especially if there's a very large environment. And it uses a queue data structure in order to be able to do this. Data structure. Okay, it uses a queue. I'm not going to explain this. There are so many awesome other videos, or hopefully maybe I'll make another video where I do explain each of these types of things in detail. But effectively what it's doing is it's coming down here and it's finding a path. But in order for it to be able to find the path, it has to figure out essentially all of the paths and figure out which one's the shortest. That can be, take a lot of memory because it has to remember all of these different things. Again, I'm not going to explain exactly how it's doing it, but it's it's going through each set and figuring out what is the best path. And so then it might figure out, okay, well, the fastest path to the player is like this. And also you have to kind of determine if it's going to be moving like this, or if it's able to move like in this kind of Euclidean direct line toward the player. That's another topic for another time. And it's kind of fun, right? This whole idea of like Manhattan distance, as in like, you know, because like you can't go walk through buildings. That's what it's called, Manhattan distance. Okay, I'm getting aside for myself. Is that the term? Who knows? Then there's also depth first search, or DFS. And depth first searches doesn't always find shortest path. Uses less memory than the breadth first search, and it is sometimes faster. Not shortest path faster, but like it figures out the solution faster than breadth first search. Uses a stack data structure. And you might be like, well, if you're not going to explain how it's using a queue or a stack, or what the heck a stack or a queue is, then like, isn't it kind of a waste of time to say this, and kind of a waste of time that you're even saying what you're saying about what you're saying? And the answer is yeah, it kind of is, and I'm sorry for wasting your time. But if you somehow are able to stick it in your memory somewhere, a lot of times at an interview, they'll just be like, what kind of data structure does the depth first search use? And then you can be like, ooh, a stack. And then they'll be like, ooh, you're hired. If it's like a really, you know, not a very big agency. They just like, you know, looked up interview questions online. You know, that sometimes happens, people. Okay, let's continue. But let's talk about the ones that are kind of more pertinent to game development. So one of those is called, if I can spell this correctly, Dijkstra. Dijkstra's algorithm. Dijkstra's algorithm. Got an algorithm named after him. Good job. So basically how the Dijkstra's algorithm works, it's similar to the breadth first search, as in finds the shortest path, which is cool. Finds the shortest path. Similar to depth first search, it actually works a lot the same way. It uses a queue, but a different kind of queue, priority queue. Okay, priority queue data structure. So basically how this works is, and how it's different than breadth first search, is unlike breadth first search, Dijkstra's algorithm is, oh my gosh, is my face in the way of this? Okay, hopefully you can see this now. Anyway, Dijkstra's algorithm is able to include what we call edge weights. Can take into account edge weights. Okay, edge weights. So an edge weight is basically where you get to determine if some of these squares are more costly than other squares, right? And so, for example, let's say that green squares, see, like I'll just like dot, 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 like these little squares, I'll zoom right in, and that actually made everything worse. I'm immediately regretting this decision. All right, so you got green squares, and green squares represent maybe a cost of just one, you know, unit of distance or something like that. And then let's say squares inside of this graph, and I'm representing them as points, represent a cost of 2 or something like that. See, now this is useful for creating algorithms for determining what's the fastest path from, you know, like one city to another city, because one city might have like more stoplights, right? It's shorter distance but has stoplights, right? Or it's shorter distance but it has tolls or something like that. So Dijkstra's algorithm is highly useful, and it's also useful in games. See, when you can put in like some red dots over here. I'm making it look like the obstacles have to do with these dots, but they don't necessarily have to do these dots, right? And the red dots mean it's like 5. It costs 5 to be able to traverse those dots. And how this works in a game is because maybe this is kind of like a mud pit, right? It's kind of just made out of mud, and so it takes longer for you to get over them. Or maybe you take into account elevation, right? So it's flat. Your path graph is flat, but you have this concept of like elevation and mountains or something like that. So you choose dynamically like how much weight that puts into that individual position in, you know, GPS and two-dimensional space or something like that. And so Dijkstra's algorithm might not consider this to be the fastest path or the shortest path because it's potentially slower, right? Like, let's say that these are actually green squares, right? Green, 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 green. And so it actually might be slower, or sorry, might be faster to go this way with Dijkstra's algorithm because there is, it's less costly per unit of distance, okay? And that's useful for games. You know, that can be very useful for games because you're determining, you know, it could be something that's more dynamic than just distance. Very cool. Okay, so that's Dijkstra's algorithm. But the important thing to recognize about Dijkstra's algorithm is it can be slower and more memory intensive because it's going to find the shortest path. And in order to do that, it has to go across each. See, if it's very big, it can be pretty costly, right? Because it has to go to each node, right, to figure out if for sure it found the fastest path or the shortest path, right? So anyways. So here I'm going to add in golly and a half. I think I need to create spacing. We're going to talk about A star. Okay, the A star algorithm. It's pretty cool. This one's the most popular one in game development. Okay, you've probably heard of it before. You know, and at this point you might be like quitting the video. It's like, A star. I heard it's AI and it's scary. It's really not that scary, and especially because you're probably not going to be the one to write it, because it's been written a million times. It's probably built into the game engine. I'll talk about that in a second. So how does A star work? A star is pretty cool. So it's similar to Dijkstra. It can, but here's the big thing about Dijkstra, or sorry, about A star, is that it's variable. How accurate or how fast? Okay, so if we're talking about fast. Fast versus accurate. So Dijkstra's algorithm is accurate, right? So if we're talking about, let's do one of these numbers. So fast versus accurate. So when I say accurate, I mean full on Dijkstra. And it can be that. Your A star algorithm can be full on Dijkstra. It can be totally accurate, find the shortest path. But you have the ability to choose fast, as in it'll find the solution more quickly, uses less processing power. And the extreme would be like full on greedy, right? A greedy search algorithm, where basically it just like every step of the way, it'll just be like, okay, what's the maybe the fastest way to get to the goal from this step. It's like, okay, left, because it's like, you know, I know where the goal is. It's over there. I'm going to go to left. Right? And then it's like, oh, drats, there's a wall. Right? You know, it could find a very not short path, but it'll find it quickly. And you can do that. And I'm not going to understand the functions that are involved in this. It's very interesting and very cool. And I recommend looking up a different video if I don't have one yet. And even if I do, look at other videos too. Come on. So you get to choose between fast and accurate. And why that's so awesome, especially for games, is because games, these types of scenarios are dynamic. You don't have to just choose fast or accurate. It can scale with the game. So, for example, you can have it dynamically adjust. So, dynamically adjust based on the scenario. So, for example, let's say you're adjusting the algorithm based on the CPU load, right? You know, CPU load or something like that, or perhaps even frame rate. So if the game's frame rate dips, then you can just keep on making that happen. Hopefully you can read this. If the frame rate dips, then you can go for fast, right? Or something like that. Or go faster automatically, dynamically. It'll scale it. So that's pretty awesome. There's other ways that you can do this. Oh my good golly and a half. I think I'm gonna see, it's like not letting me type without it. No, it is. Okay. I'm not gonna push my luck. All right, or perhaps it'll be like environmental, right? So based on environment. So for example, perhaps like you know for a fact that it's a very costly terrain, right, or something like that, or there's a lot of mud, you know? And then you can choose like how fast or accurate you want the algorithm to be based on if everything is uniformly muddy or uniformly grassy or uniformly, you know, traps everywhere, or whatever it is you want, and you can tweak your algorithm based on that, whether you want it to be fast or accurate. Also, if like depending on how close you are to the goal, the closer you are to the goal, who cares if it's accurate, right? Because it's like the path to the end result is probably not going to matter if you're pretty close, anyways. You know, but you have the choice to be able to select. And A star usually picks the best path or close to the best path much more quickly than Dijkstra's. So A star is just much more efficient, typically, and therefore it's the most common type of pathfinding algorithm that we find in games. Now here's the thing, you might already be kind of scared. Like I said, like maybe you're not scared, but maybe you're already scared because then it's like, oh no, I have to learn this algorithm. But here's the thing, most of the time you don't actually have to learn it because game engines have this junk built in. Okay, so for example, coming back to this little fun thing, maybe I'll just create another thing just because, you know, drawing is fun. And you watching me draw is not fun, so I enjoy that. No, I'm kidding. All right, so we have our character again. This is big. I don't know why I made it so big again. We got our little character, little smirk, and so on. Then, of course, you have your mushroom monster. And you have your obstacles in the level. So I'm going to introduce this concept of what is called a navigational mesh. Hello. All right. Navmesh. Navmesh. You may have heard of it. So navmeshes, in a lot of ways, kind of eliminate a lot of the kind of work that you have to do. Navmeshes are very cool. So what the heck is a navmesh? So a navmesh is essentially just a collection of contiguous convex polygons. Okay, so what the heck do I mean by that? Adjacent contiguous convex polygons. So I'm going to do this in blue because whatever. So what happens is you have a mesh, and so a mesh is really just a bunch of different polygons. And let's say that in the game engine you're saying like, okay, I want my nav mesh to be as big as the environment. And so then what the game engine will do, and you might have to manually do depending on the game engine, but most game engines will do this automatically, it will then split it out into the contiguous polygons, the convex polygons. So it'll be like, oh, here's a polygon here, right? Here's a polygon here, just like across the whole thing. And then there's like a polygon, I guess this might not be the right size, a little polygon here, there's a polygon here. It's just drawing out these polygons. They might be triangular because, maybe not all the obstacles are rectangular and so on, but it creates all these different polygons, which is pretty cool, right? And here's your nav mesh, right? It's your contiguous, it's like all connected together set of meshes. Of convex polygons. Now, they're not concave because the concave, you'll understand why they're not concave here in a second, but if there are any concave types of scenarios, you just turn them into multiple convex polygons. So how this works is this. If these are, by the way, the objects that are looking for paths inside of the nav mesh are called nav mesh agents. Okay, they're called nav mesh agents. Agents. Okay, so agents are the things that are looking for, paths to their goal. So this enemy perhaps is a nav mesh agent, and perhaps it's it perhaps is right here, right next to the player character or whatever. And so is it going to use some kind of fancy algorithm, Dijkstra's A star? No, because how it works is that if both the goal and the agent are within the same polygon, then there's no obstacle. So all it's going to do is just go to the direct path. The direct path is the shortest path. It's going to just go directly at the goal position, because there aren't any paths it needs to figure out. The shortest path is always just going to be a straight line, unless we're talking about a grid, in which case it'll do that, Manhattan distance thing, which can be anything, right? Manhattan distance is going to be the same speed if it's doing that, or if it's doing that. Go ahead and make a grid and figure it out for yourself. It's the same distance. It's pretty neat. But the point is that it'll just go in a straight line, typically speaking. But if it's not, right, so if the agent is up here, then in order for it to get to the goal, then it will go into the graph search algorithm mode if the polygons are not in the same, if the goal and the agent are not in the same polygon. So then what it does in order to be able to do that is it doesn't do it at this point, it does it beforehand, but the mesh is essentially a grid. Okay, I'll make that grid into green, right? No, I won't. The grid, just assume, are these points, right? These individual points, right? These points. So it will turn it into a grid. Pretty cool, right? So it gridifies it. And if it's three-dimensional, maybe it'll voxelate it, right? It'll turn them into three-dimensional grid, like voxels. Because in order to determine whether an object, such as this mushroom character, can fit between polygons, it needs to know how many points are between those spaces, and it'll have a center point, and then you can determine what is the width of the agent, so to speak, so that it can determine if it's able to fit between different obstacles, right? So that's how it does it. Very, very neat. And if it's not able to fit between different spaces, it's possible that you defined your grid spacing to be too large, right? The points between the grids might be like boom, 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 and so then there's only one point here between these obstacles, and it's like, well, I can't fit there. So you have to kind of reduce the number of points. I'll talk about that in a second. But see, the point here is that essentially what it'll then do is it will turn, your nav mesh into essentially one of these types of environments where you can perform a graph search algorithm to the goal's polygon. So effectively, you're just going to the various polygons, and by doing that, it's actually really easy because you can do all sorts of other types of optimizations. You can first have kind of more of a broad search by having fewer grid points. You're checking every other grid point just to see if you're able to get to the next polygon. And then if you aren't able to, perhaps, then you can shrink it down. So it's pretty neat. And again, I can't talk about too many of the details right now. I'm already getting ahead of myself, or getting too detailed with myself. Anyways, and then once it gets to the the polygon in which the goal is, then it can go in a straight line, do whatever it needs to do. Okay. It's actually very quick, and it can calculate these things very quickly, and it has to be able to do that because a lot of times an agent is continuously calculating its goal, very, very frequently. It's not interested in the perfect path. And once it goes to this graph search mode, it will then, use A star. So typically speaking. Pretty neat. So that's the idea of a nav mesh. But why this is so important to recognize is that it's easy frickin' peasy to implement in most game engines. Easy to implement. See, all you have to do, all you have to do in order to be able to implement it is to just choose your nav mesh. It depends on the game engine. Just draw a big old box, and then you determine what are the obstacles. Perhaps they're static bodies or objects or something like that. And it'll be like, great, here's your nav mesh, and you're done. And then you basically just hit beep boop boop, and it'll do its magic. You have it set to say find path, and then move along that path or something like that, right? It depends on the game engine. But the point is, it makes it very simple for you to be able to implement. You're not the one implementing the A-star algorithm or anything like that, all the other stuff that's happening behind the scenes. All you're typically stating is like, is there like stairs? What's the stair height so that it can like go up and down stairs? Okay, so it's easy to implement, but it's also flexible. So when I say it's flexible, I mean that you can do some cool stuff. You can sometimes tweak edge weights. So when I say edge weights, remember I'm talking about costliness. So you can say like in your navmesh, depending on the game engine, you can say like this area is, you know, more costly, or this area is more costly. You can choose which areas are more costly. And so then it will choose the best path depending on the accuracy of, you know, that you've chosen for your A-star algorithm, which also is potentially exposed to this whole system of navmesh. And then it'll choose based also taking into account how costly certain areas are. Also, you can typically choose the grid or voxel size. So you can choose how many points, like the finer the grid, or, you know, the smaller the grid and the voxel size, the you know, more the more CPU costly it is, like the more demanding it is on the CPU, right? Now, sure, you can do some parallelization, especially if you're doing something like Dijkstra's algorithm, because you can have it set to different threads to like go here, try this one, try this one, try this one in parallel. Maybe the game engine's doing that, maybe it's not, depends on the game engine, but in any case, it can be more costly. And so what you do first is you choose like a pretty large grid size, pretty large voxel size. If it's good enough, then it's good enough. If it's not, and things get stuck and it can't find paths when it should have been able to, then you can reduce the size. So it's pretty cool. And you can just do that on the fly right there in the little editor. It's super neat. All right. So the point here is that the whole thing about pathfinding is, for most, you know, just gameplay programmers, you really don't have to understand like very complex AI programming. Now, sure, understanding these algorithms is probably going to be better off for you, especially in a job interview, because they're probably going to choose the programmer who understands algorithms better than you, or I mean, better than the other one, better than the other people who don't understand them as well. But especially if you're creating indie games, then unless you're creating a more complex type of pathfinding type of game, it's often enough to not to just use navmeshes and just the built-in tools. All right, so I'm now going to kind of change tracks here for a second, because we talked about pathfinding, we talked about finite state machines, but it's really not as simple as just pathfinding or finite state machines. It's usually a combination of both. Right? It's not just one or the other. It's kind of both and intertwined, right? Because, you know, like, sure, the enemy can go through the maze. It can be like, but what does it do once it gets to the point? You know, it's doing something. And so it's part of its state that is going through the maze. And it can stop going through the maze or change paths or do something else. Or what about if there's like a door, right? Like, what if there's a door here? Oh my gosh, that could be tricky. It's like, does the enemy open the door? Does the enemy notice the player through the door? You know, like, there's a bunch of stuff that has to be asked, and these have to do with the state of the enemy, and the state, and also whether or not there are paths available. And those two things are intertwined. So, with that being said, what does that mean for us? So, even in the simplest case, where the enemy just touches the player dies. In this case, like, that'd be kind of intense, right? Because, like, what is this, frontier justice? The enemy just kills the player once it sees the first sign of criminal behavior. Anyways, but even in a game like Pac-Man, right? So we have Pac-Man, and in that game Pac-Man, right, you got these different, like, grid things, and then you've got, I forgot their names, Angry... That's not its name. I know the pink one. I don't have a pink pen. We'll just use the rainbow pen. There's Pinky, there's Blinky, I think is blue, and I think there's like Clyde is orange, and then there's the other one. Binky, Trinky, Stinky. Someone please tell me in the comments. And these ghosts, like, sure, when they touch Pac-Man, you lose. This game was like freaking late 70s, and it was pretty advanced because it wasn't just that simple. Each stinking ghost had its own pattern, its own behavior, its own different pathfinding algorithm. It's like, what the heck? Yeah, like Clyde just does random junk. The red one, Fury, we'll call that one for now, just like chases the Pac-Man relentlessly. Blinky just does random junk. No, he doesn't. I think Blinky's just kind of unpredictable. I don't remember. Pinky's just, does some sneaky trap stuff. I'm not sure. But anyways, the point that I'm trying to say here is that if I'm coming back to this whole like contention that I have about game designers this is the worst Pac-Man drawing in the entire world, by the way. I dare you to find a worse one. If we go back to this whole idea about game designers, even in this game where like, oh my gosh, each of these ghosts have like a different pathfinding algorithm, that seems very complex, and it is. And I commend the programmers who worked on this game, programmer and then like hardware, designer person. But did you know that the person who came up with Pac-Man was the designer, not the programmer? I think this person, what was their name? I think I wrote it down. Toru Iwatani. Anyway, was maybe one of the first, or maybe the first, exclusively game designer on one of these big games. Okay, so that is to say that unlike all these other kinds of games that had come out beforehand, which were just like programmer designer people that made just very simplistic games that had enemy AI, so to speak, no coincidence that it was a game designer who had come up with this kind of idea and came up with the idea of having different behavior depending on which ghost, and was able to define how these ghosts work and how they scatter sometimes. So it's these different state machines where sometimes they're in scatter mode, where they scatter around to give some relief to the player, and then sometimes they're in chase mode, sometimes they're in runaway mode, and there's different states for a game like Pac-Man, right? I almost want to write this stuff down, but I also don't. All right, we'll just use this abstract portrait, hang it in your wall. The point is, it's very much a designer thing that we talked about those different paths, and the programmer potentially wouldn't have come up with those different ideas and wouldn't have been able to implement those ideas if they didn't have the direct instructions and tweaking as suggested by the designer. And then sometimes the designer sometimes there's the question of, is the AI convincing or believable? Right? So if we're just talking about like a platformer game, then who cares, whatever. But if we're talking about a game where, the AI is supposed to like resemble natural human motions and decision making and this kind of stuff, not to the level of like, machine learning kind of stuff, but rather just that it looks believable. So even if you're a programmer who made a brilliant implementation, it's perfect. You created a perfect pathfinding algorithm. You created perfect artificial intelligence for this enemy NPC or something like that. But you know what? Sometimes it's too perfect, right? Sometimes the AI, and this is more of my educational rant, sometimes AI is too perfect. It's kind of like this uncanny valley of AI where like it's so perfect it just doesn't seem natural. It's like, that's not how things work. Sometimes you want the AI to be kind of dumb or not find the right path or be able to trick the AI. Right? And so because of that, that's something that the designer is going to be able to decide. You as the programmer is like, look at my perfect algorithm. But the designer's like, it is able to point out perhaps how it is able to nitpick, right? Perhaps the designer will nitpick the programmer to say like, well, this element like doesn't feel natural, and that's good. That's what you want. You want your designer to be able to nitpick, and if they can articulate and identify and articulate what those unnatural moments are, concisely, and specify them for the NPC behavior, then you got a good designer, right? Because then you can implement those things. because ultimately it's the specification that's some of the biggest challenge, maybe even the biggest challenge, right? Because once you have that information, you can then apply it, which is pretty awesome. Or you might even write the tools. Oftentimes that's what happens. As a tools programmer, you'll write a tool that the game designers will use in order to be able to tweak those variables themselves, right? And so ultimately that might be what you're doing. And they're the ones who are creating essentially the complex algorithms. You just gave them the tools to do so. Okay, so it's pretty neat. But even in the scenarios, okay, even in the scenarios, what am I trying to say? That you have the most well-designed, the most efficient algorithms, you've taken into consideration all of the different specifications, you're going to come up with this whole thing of edge cases. Okay, you're going to have edge cases. And so ultimately, it's not how brilliant and tightly packed your pathfinding algorithms are, or even your finite state machines, because you're going to have edge cases. Edge cases are where something is just not working correctly, right? And those edge cases crop up in the designer saying, like, this feels unnatural, and it's like, well, that means I'm going to have to adjust the, state machine to account for that specific scenario that you're talking about that feels unnatural, and that's an edge case. But even more edge cases crop up as soon as you start getting reports back from the playtesting, right? The playtesters are going to be like, there's a lot of problems with the enemies running into walls and things like that. And then you have to kind of sometimes tweak these. Even if you have a great pathfinding algorithm, sometimes you're going to have edge cases where just the blend of these different elements just doesn't work correctly, and you have to kind of fudge in these specific scenarios. Like when the mushroom enemy is in this particular situation where the player is doing this particular thing, like the player's unlocking like a door, and we just don't, like, all enemies stop working for a second. It's an edge case. And you have to come up with those types of, you have to solve those edge cases. And you know what? Oftentimes the best way to solve an edge case is to just hard code it into the finite state machine. And you might think, like, that's ugly, I'm just going to refactor everything. Well, oftentimes you don't have the time to do that, you're not able to do that, and when you do it, you realize, oh great, now there's other edge cases, or even some of the same edge cases. So this doesn't necessarily solve the problem, and sometimes, your code that you ultimately, you're starting to feel is getting really messy is necessarily messy, because the game, to feel natural and to handle all these different scenarios, sometimes can get a little bit messy, and that's okay. All right. Anyways, the last thing that I want to talk about is this whole idea that some of you may have heard, which is emergent behavior. This idea of emergent behavior. I'm just going to draw some more down here. Emergent behavior. And see, these are kind of fancy words that you might hear. It has to do with artificial intelligence to some degree. But the reason why we're talking about emergent behavior is because sometimes a designer isn't able to fully calculate how all of the gameplay is going to work out in the game. They're not just able to foresee how all the gameplay dynamics are going to play out. And that's sometimes by design. Okay, and that's okay. That's part of the designer's decision. So how emergent behavior works is that there's these different nuclear systems. So there are these little systems that are well enclosed in their own, they work within an environment without other systems necessarily affecting them. So for example, I talked about how we have this little mushroom monster and is on a platform of some kind. And we already said that it had this kind of behavior where it moves left and it moves right, and it jump bite attacks. Okay, so that's its behavior, and it's based on the player. But perhaps it also behaves based on other enemies, because let's say it's indiscriminate about what it's attacking. It doesn't just attack players. So if you have two of these, and one's going this way and one's going this way, they run into each other, they attack each other. But then if you put the player in here, then what's it going to do? Right? Is it going to attack the enemy? It's going to attack the player. You could probably make a prediction because the systems are relatively simplistic. But as soon as you make these systems less simplistic, like for example, like a game like Red Dead Redemption 2 or something like that, where all the enemies, all the NPCs all have very complex, behavior patterns. When you start putting them all together, you can get some really interesting, unexpected scenarios, right? Where the characters are behaving in a certain way just based off of the rules that they're set within their patterns. Okay, and so the designer doesn't necessarily anticipate it. So they just kind of throw all these different characters and systems into a game, like what happens when there's like a snowstorm, etc. Plus this, plus this, plus this. We aren't able to predict it. And this is part of the whole thing about, game theory and our economy and all this kind of stuff and, war games and things like that. But this also exists in games, and sometimes it's by design. And even in those scenarios where the designer didn't foresee exactly how the emergent gameplay would unfold, it's still there on the front lines, tweaking and setting behavior to and changing behaviors within these nuclear systems in order to produce more interesting or desired results through the playtesting. Right? And that's a lot of times outside of the programmer's control. It's really, again, even with emergent behavior, it's really a designer's decision. Oftentimes, they're the ones leading that. And you, if you're the programmer, are essentially just kind of giving them the tools to be able to manipulate it, or you're doing it based off of specification. All right? But ultimately, a lot of this whole thing about artificial intelligence is oftentimes it's just associated as like a programmer specific type of topic, but it really isn't, because we're talking about designing patterns and conditions that have been predetermined within those systems, within individual systems. And a lot of that and most of that is really just outside of the programmer, and it's mostly a design talk. So in conclusion, I don't want you to hear the term AI programming and freak out, okay? Yes, there are people who identify themselves as AI programmers. In fact, you'll see job postings that say AI programmer, and if you don't know how the A-star algorithm works, then don't apply, probably. But that's it's a niche field, AI programming. If you're trying to become an AI programmer, then sure, if this is your first video, great. Watch something else after this. But ultimately, for most programmers, most gameplay programmers, they're not going to have to worry about a lot of this type of stuff that we've been talking about. Most of it's already handled by the game engine. It's the types of finite state machines that you're creating for these different systems are also assisted by the game engine and are relatively rudimentary. And so what's more important, in my opinion, this is my second hot take. It's not that hot of a take. But what's much more important, in my opinion, is focusing on having a good code architecture for your game, because the code architecture is more fundamental to all games, and it's harder to fix once you've gotten pretty deep into the development of the game. Okay, once you've gotten pretty deep into the development of the game, you can't just like slap on a different algorithm or, it's essentially the backbone of your whole game. And so if your code architecture is not working, all the rest of the stuff is not going to work, and it's going to grind to a halt. So I would focus on getting better at understanding code architecture so that you can define the data structures, you can define the generalized types of systems and algorithms in your game on top of that foundation. All right, that's all that I have for now. Thank you for watching the video. If you enjoyed it, you felt you learned something, then like the video, leave a comment below if you like, and subscribe if you want to see more content like this. Awesome. And until next time, I'm wishing you peace.